Hello everyone. So today we'll be solving a LeetCode hard problem, minimum number of moves to make palindrome. So the problem states that we are given a string S consisting only of lowercase English letters, and in one move we can select any two adjacent characters of S and swap them. Now we need to return the minimum number of moves needed to make S a palindrome, right? And it is guaranteed that S can always be converted to a palindrome. Okay, so I hope you know what a palindrome is. So for example, a string of the form like A, B, C, D, and so on, and this should have a corresponding pair on the right. So D, C, B, A. So this form of string is a palindrome, supposing that this subset is also a palindrome. Okay, now what move we can do? We can swap any two adjacent characters in one move. Okay, now we need to return the minimum number of moves to convert the given string into a palindrome, and the constraints are of the order of 2e3, and it only consists of lowercase English letters. So for this problem, I will tell you how you can think in the direction of dynamic programming approach initially, but why it will be failing in this case, it will be incorrect in this case, and means how will be optimizing, means leaving the dynamic programming solution behind and solving it using a greedy algorithm, and I will be proving it as well. So why dynamic programming will be an overkill, I will be discussing it, and how means changing states will not be possible here, and why we need to move from DP to greedy, because since you can see like return the we need to minimize something. So whether when you need to minimize or maximize something, we generally try to think of a DP if we are given like some subsequences or substrings we need to handle. So you may think of it as a dynamic programming problem, but I will prove you why that approach will fail here, and then we'll be discussing the correct approaches. So let's see the first given input first. So suppose we are given the string as this. So a b b. Now we need to make this a palindrome using adjacent swaps. So for example, suppose we fix this A here and we want A on the right. So what we can do is we swap this to this and then swap this to this. So we move this A two steps forward. So how many moves we needed? Moves equals to 2, and the new string will become A, and this B means first this B will come here and then this B will come here. So the final string would be ABB. And as we can see, like this string is a palindrome, hence 2 is means a valid output. Again, let's try different ways of making it a palindrome. Suppose here we fixed A, now let's fix B here, right? We want a B on the left. So we want, since we want a B on here, we'll be making, means swapping this B till it reaches the start. So we'll move this B here and then here. So again it will become, since B will reach here, this A will move to there and this A will move here. So the final string would be BAAB, and again the moves that we have used is 2 only. Okay, now let's see for this input how we'll be solving it. So we have the string as LETELT. Now again let's fix this L here and try to find a L on the right. So we see that this L can be moved rightwards. So we will perform one swap. So moves equals to 1, and the new string will be LETETL. Okay. Now this position is sorted. So we move to E. Now for this E, let's again try to find some E on the right. So we'll move this E to the right. So the moves will become plus 1 more, and the new string will be LET. This T comes here, so TEL. And as we can see, like this string is a palindrome, and the number of moves taken was 2 only. Let's try something else. LETELT. Let's try to fix T here. So we need to move this T 2 steps backward. So the new string will be this T moves 1 step backward. So this E comes here and then L will come here. So the new string will be T, then L, then E, and ELT. So as you can see, like this string is also a palindrome, and the moves that we have used is 2 only. Okay, let's try to see a new example as well. So we have, suppose we are given A, C, B, B, C. So let's fix this A here. Now when we try to like find means A for at this position, will not get any position because this n is odd here. Okay, and since n is odd, the palindrome will look like something x, y, z, dot dot dot, a dash, and dot dot dot, z, y, x. That means this center will not have a corresponding means pair on its side, right? Because this is a odd length. So means n by 2 pairs and plus one center will be there in palindrome. Okay, so how do we deal such cases where the means a pair does not exist on the right or on the left? So what we can do here is follow the same algorithm that we tried to follow above. First we tried to like see for a, we fixed a, and we try to like find a from the right so that we can move that a to the end, but we do not find any a other than this a. Okay, so what we can do, we can fix this c here and then try to find a c on the left. We can move to the start, so we'll use this c and move it to the start. So the moves will increase by 1 and the new string will become c a b b c. Okay, now we have reached this state, like the new string is this. Okay, now again we can either fix this a or we can fix this b. So let's try a different one this time. Let's try to fix a this time. So if we fix this a, then again we'll not find any a from the right which we can move to the end, right? So that will not be feasible. So let's try to fix b here. Now for B, we'll find from the left the first B that we can move to the start. Okay, so the new means we'll move this B here. So we'll get C, B, A, B, C. And the moves will increase by 1 and hence the total moves here will be 2 and this string will be a palindrome. So we saw that it is not always possible to get an element on the right or on the left which will be moving to the end or to the start, right? So hence we need to handle those cases as well. So for handling those cases, we can like try fixing the first as well as fixing the means last element alternate wise, and then finding out the minimum of these two. So like this approach, like greedy, is more arguable kind of thing, like whether it will always means give us the correct output or not. Before like moving it deep diving into the proof of this approach, I will try to like explain you why why means DP fails here. Okay, so here you might think of a DP approach like you can create an state in the form DP of I comma j, which denotes like minimum moves required to make string I to j a palindrome. Okay, so this means this state you can think of. Suppose now what will be the base case? Suppose we are given an strings, the same string AC BBC. Okay, AC BBC. Now what will the base case? So base case will be like suppose for one length strings, one length strings. So one length strings, it will be like dp of I will be 0 because all one length strings will be a palindrome one, right? Now let's try to see for two length. So for two length, we'll see like we need to find suppose dp of 0 1, 0 1 2 3 4 number of moves to make this string a palindrome. We cannot make this string a palindrome, right? So we move to dp of 1 2. So this is not means suppose equals to minus 1. Then we go to dp of 1 2. This is cb, so this is also not possible. Then we go to bb. Okay, so dp of 2 3, which is possible, hence it is already a palindrome, so it is also 0. Then we move to dp of 3 4. Since again making this string it not possible a palindrome, so it will also remain minus 1. Now let's go for three length strings. Okay, So we need to make this string a palindrome. Now what you might think, like if you want to solve a problem for dp of ij, then we should only means need to handle si means string of I and string of j, and like suppose str of I is the same as str of j, then what will be the dp of I comma j? Dp of I comma j will be simply, if we have the index I here and the index j here, then if though both these values are true means equal, then what will the answer? The answer will be, since this means extending this string on both left and right will still remain a palindrome, so it will be like dp of ij will be dp of I plus 1 and j minus 1, right? So since the answer of this will be the answer for dp of I comma j, so we have handled one case here. Now what about the case where str of I is not equals to str of j? Okay, so in this case what we'll do is we need to like for suppose we fix this I. Okay, so we have I here and we have j here. Now so string of I is not equals to str of j, so we need to build, suppose this character was a. Okay, now we need to find some a inside and need to bring it to the end, right? So how this like will not be able to solve using dp is because the new sub problem that we are creating is for a different string. Because suppose we move this a to the end, the new string that we'll get for dp of I plus 1 comma j minus 1 will not be the same as the problem that we solved, means as the sub problem of dp that we already solved earlier. So we cannot reuse this state because string I plus 1 to j minus 1 will be different now. Alright, so that's why like since we need will be requiring to modify the internal substring that we have for previous subproblems already solved, we cannot like reuse the solution because this string will be modified. Alright, hence the dp solution, if we try to means use dp here, it will fail here. Okay, so I hope like you get how like initially you might think of dp, but this is why it will fail because the smaller sub problem will be changing here. Now again we'll try to see the means the greedy approach that we followed initially. So what we are doing were a c b b c. Okay, what we are doing at each step, we are fixing when first fix left, and then from right find character equal to left to move it to the end, move it to the end, right? This is what we are doing. And in second step we are fixing right, and then from left find character equals to right to move it to start. Alright, this is what we are doing. For example, here first we fix left, then try to find a from the right, but we are not able to find anything. But then we fixed c, and from left we try to find c, and as soon as we find c, this will be the c that we will be using to move it to the start, right? Now how like this approach is correct? Why? Because at each step we are obviously means not using redundant operations. So for example, if s of l is already equals to s of r, then no swaps performed. Alright, no swaps performed. And if s of l is not equals to s of r, then also what we are doing, we are like, suppose we have this string from l to r and we fixed a here. Alright, and this was like b c, then we had a, and then some strings, then again a, second a, right? So we are never like using swapping this A to cross this second A that we have. We'll always be using this A to move to the end, right? So we'll never perform redundant swaps like moving this swap, moving this A to swap with this A, right? This means no redundant operations will be performed here, right? And obviously like if we have x and x here, either we'll move like x to this position by a distance of z, or we will move this x to outwards by a distance of z. So this z distance will remain the same only. Okay, so hence like this proves like how always using the first same character that we encounter for the looking value will always like give us the overall correct optimal output of the minimum number of moves. So this is the approach that we'll be following here. Um, so the approach will be like we'll simply take two pointers, one pointing at the start and one pointing at the end. Now what we will do is, if s of l is equals to r, then no operations need to perform. So we will simply reduce, means increase l and reduce r. Okay. And else if it is not equal, then what we will do is first fix left. Okay, once we have fixed left, like find s of l from r, and the number, suppose string was l to r and it was a. Now we need to find a from the start. Suppose a was present at this point, so we'll move r till we find this a. Suppose this is index r. Okay, so what is the number of swaps that I will need to perform is the number of the distance between these two. So for example 1, then 2, then 3. So this will be the number of swaps I will perform. So swaps will be r minus index r, right? Now let's also try to fix right, because what if we did not, like what if this a was not found anywhere else? So the distance will be, swaps will be r minus l only. That will be the case where odd length palindrome, right, as we discussed previously. So for odd length we'll need to like we'll traverse through the entire string, and the operations will be r minus l, which is not feasible obviously, because this a needs to move to the center. So obviously we'll try to look, fix the right, and then if for this a there did not exist any a in here, then it is sure that for this x variable there will exist some x variable in here. Because why? Because it is given in the input that making it a palindrome is always possible. So if this is the center, means center element which will be moving here, then obviously this x will have some element in here which can be moved to the start. So I hope like you get why means fixing one of them will means give us some swap value which is less than r minus l. Okay, so when we fix right, we need to find, means we have fixed right, so find s of r from l. Okay, so what we'll do, we have l to r. Suppose a was here this time, so we need to find, means move this l till we find this a. So suppose this index is called index l. So again the number of swaps that you need to perform is the number of steps between l and index l. So it will be like swaps equals to index l minus l. Okay, now at each step we'll find out these two swap values, and whichever swap value is minimum we'll perform that, so that greedily we are minimizing the number of steps required. So this is what we'll be doing. We'll calculate these suppose swap l value and swap r value, and whichever one is minimum will update the given string. So we'll perform the swaps, and after we have performed the swap, the new string will be like this lr. So these positions will be equal, so we'll decrease these pointers so that the new, means new modified string will be applying the same algorithm for the updated lnr. Okay, and I hope like this approach is into your head. For example, as we see, means let me see again, tell you the approach that we followed. So for example, here we fixed l. Alright, then we moved this l here, since it only took one operation and if we try to fix this t, then it would have taken two operations. So since 2 was less than 1, so we move on with this. Okay, so the new modified string was this only. Now we need to apply the same algorithm to this modified string. Okay, now for this again we fix this e and find out the first e from right. It will be, means one swap will be required here, and if we fix this t, then again we'll encounter t after one step, so here also one swap will be required. So we can do either of those things, and again it will lead to a palindrome only. And after we have done this, the L and R will be here, and since both are already equal, the loop will be, means terminated. So we'll be executing the loop till while L is less than R, and yeah, and we'll be greedily calculating the number of swaps required. So I hope like you get why this means DP approach failed, and how we tried to use means tried to satisfy the condition for outermost indices, and then moved inwards and satisfied the conditions greedily at each step, so that the means the minimum steps required is minimum. So I hope like let's see the code, and I hope we'll be able to means get the result. So we fixed these two pointers L and R, and this result will be calculated storing the number of moves. Okay, now if both are not equal, then we swap left character. So we fixed the left character first. Now we need to find this. We fixed this left character. Now we need to find some means index L, which is s of index L, which is equals to s of R, right? Okay, so we fixed R, and we need to swap this L. Sorry, we fixed R first, and then we need to swap this L. So we need to find some index L such that s of index L is equals to s of R. So we find this index L, and the number of swaps required will be R minus the number of swaps for left count will be the number of, means the number of steps we have moved this. So it will be swap left count will be index of L minus L. And similarly we fix the left character, fix the left, and we'll try to swap this right character. So we try to swap this right character, and we move it till we get a index R such that s of L is same as s of index R. And again here the number of means swaps required will be R minus index R. And then if swap left is, means swap left count is swap less than swap right count, then we'll actually perform the swaps, so that this overall strings gets modified, and we will perform the same operation on the new modified string. Okay, so this is what we'll do. We'll increase our result by swap left count, and while this index, means the index L that we have found here, okay, we'll swap these adjacent variables till we reach here. Okay, so I will create a loop from index L to N, and I have swapped it from the end. So this swap these two variables, and swap these two variables, and swap these two variables. And if means right swap was less, we'll start from index R here, and swap the adjacent values till we reach the end. Okay, so this is what I have done here, and in the end we'll simply increase the left pointer and decrease the right pointer, and finally return the result. So the overall means time complexity for this approach will be the external loop will execute till big of n by 2, and the internal loop can go up to, means this can go maximum till big of n, because that was the case where for a, means no a was present here, so in that case we scanned the entire array, right, entire string, right? So this can go up to, means maximum of big of n. So the overall complexity would be big of n into n by 2, which is of the order of big of n square. Alright, and since like n can only given go up to 2e3, hence this will be acceptable, means acceptable in 1 second, like 2e6, so it will be acceptable 4e6. So I hope like you get how, why the DP solution failed, and how we optimized it to greedily, means fit the scenario here, and moved inwards from outwards, satisfy the condition for outward characters, and yeah, so greedily we try to satisfy the each conditions. Let's try to submit the code as well once, so to see how well it performs. And as you can see, like it runs in 12 ms, which is like of the order of n square. So yeah, it is completely fine. So I hope you got the logic of the problem, and like how to handle different approaches and how to compare those approaches if one of those approaches is failing. So you can like means doing trial and error only will help you to get to a particular solution, or derive why a particular solution is failing or why a particular solution is getting accepted. So means try to try run on your own for a lot of test cases, and then like if you are not able to solve the problem, then only means try to show means see the solution of the problem. So I hope you get the entire logic. If you have any doubts, feel free to comment down, and I will be happy to help. Thank you for watching.